All right. Good morning, everyone. I'm Karthik, a graduate student at PPL, and I'm here to present our active ongoing research in developing a highly scalable graph clustering library based on a parallel union find algorithm. So firstly, the problem that we are trying to solve. Graph clustering or connectivity is the process of detecting connected components in your given graph. So a connected component is basically defined as the maximal size subgraph where every pair of vertices are connected by a path. So an example is shown in the figure above. This algorithm is at the cornerstone of various science and engineering applications. So there are two schools of approaches towards detecting connectivity in a graph. First is performing a standard graph traversal algorithm like BFS or DFS, and the second is using a union find based approach for detecting connectivity by developing disjointed data structures on your vertices using the edge information. So we propose a new implementation, a new parallel implementation that detects connectivity in a graph based on this second approach. So this will be the outline of my remaining talk. I will start with some related work in this area, present our new parallel union find algorithm that we developed in Champ++, and talk about optimizations like path compression that we implemented, and give a brief idea about our implementation and some performance numbers. So connectivity in a graph is a very well explored and a very well solved problem. There are numerous amounts of work which are being done both in theory as well as in practice to detect connected components in parallel for large scale graphs. But among the million papers that one could cite, I here present top 4 papers that are highly relevant to the work that we are currently doing. So the first is a classical work by Shluak-Wishkin, where they present a logarithmic parallel algorithm to detect connected components in a graph using the PRAM model. Second is the work by Nasimi and Sartar Sahini, where they develop a connected component detection algorithm for a mesh-based parallel computer. Krishnamurthy and others were probably one of the first few to extend Shluak-Wishkin's algorithm to a distributed memory setting, where they used the probabilistic mesh idea to show the working of their algorithm. And more recently, the work by Mane and Patwari, where they develop a scalable parallel union find algorithm specifically for a distributed memory machine. But what we notice from the literature is that most of these implementations are highly focused or highly optimized for a shared memory-based parallel programming environment, or they're synchronous in nature. But our motivation is to develop a scalable parallel implementation that is highly suitable for a distributed asynchronous environment. And we are talking about the scales of hundreds and thousands of cores of a machine like Blue Waters. So the parallel union find algorithm that we developed is as follows. So given a graph G with V vertices and E edges, an edge E connecting vertex V1 and V2 represents a union operation. So how do we implement this union operation? First, we message the vertex V1 in order to perform the find operation on vertex V1. So find is basically starting a chain of messages until you find the root of the component that V1 currently belongs to. Let's call this the boss1. Now, boss1 messages vertex V2 to perform the similar find operation of V2 along with carrying its information, that is boss1's information. Now, when you find boss2, that is you finish the find operation on V2, you just realign the parent pointers based on any condition that your algorithm specifies. So what we are effectively doing here is we are constructing a forest of inverted trees where each tree represents a unique connected component. And the root of this tree, or the boss, is the representative element of your component. So this is a graphical representation of our algorithm where we are doing a union operation for an edge that is connecting vertex V1 and V2. Here we take a very simple approach that boss2 always points to boss1 irrespective of any conditions. So there are various challenges that we faced when we wanted to practically implement this algorithm, and one of the biggest one being race conditions. So consider the scenario graph given here. So you have 3 vertices, 3 edges, distributed symmetrically across 3 chars and 3 different PEs. So when these edges are processed at the same time, say at time step 0, all the symmetric nature of these edges is going to lead to a formation of cycle in the tree that you're constructing. So in order to prevent this sort of a race condition, we enforce a strict ordering in the union operation, say based on the vertex ID. So what we enforce is that the ID of the parent node should always be lesser than the ID of its children. So this brings in an additional min-heap-like property to the inverted tree that you're constructing, and you can detect a cycle edge if a lower ID vertex is being asked to point to a higher ID vertex, in which case you would just flip the edge and reprocess it. So based on this, we came up with some high-level pseudocode, and we decided 3 important functions that are central to our algorithm. First one being the union operation or the union request, and other functions being the find operation split into 2 as find boss1 and find boss2. These are equivalent to the entry methods that we implement for this algorithm in Charm++. So path compression is an optimization that actually comes from theory, which gives the logarithmic time complexity for the classical sequential union find algorithm. Basically, when you're starting to construct all these trees towards the later stage of your algorithm, these trees are going to be really deep. And you want some sort of a technique to shortcut the path from the vertices to the root instead of climbing all the long paths. We implement 2 types of short path compression. First is a local path compression. Here, we make sure that all the local subtrees that are constructed within the char are completely shallow, that is a rooted star. And how do we do this? During the find operation, if a char finds that the next parent on its current path is on a different char, then it sequentially updates the parent pointers of all the nodes that are on the current char on the same path to itself. The outcome of this sort of an optimization is shown in the figure here. This, of course, increases the amount of sequential work that you're doing per char, but this greatly boosts the speed of your future find operations. The second is a global path compression, where you want to short circuit the paths that are spanning across multiple chars. And this we do by doing the pointer jumping operation to a grandparent vertex. So consider the scenario over here where a vertex in char B finds that the next parent on the path is on char C. Then before sending a message to char C, it also sends a message to char A, where the first vertex started the find operation, to inform it to change its parent pointer to C instead of B. So you're technically just short-circuiting the path from A to C instead of going from A, B, C. So yes, this increases communication because you're doing more messages than they're required. But we were able to bring down the overhead of these messages by aggregating the messages using Tram library. So to give more details about the implementation, we decided to implement this entire algorithm as a library so that it can be used for general Charm applications or AMPI applications. There are 3 important phases in our library. In phase 1, you're building the forest of inverted trees using our asynchronous union find algorithm that we proposed earlier. In phase 2, you're doing the labeling part, where you identify the boss of each component and you label all vertices in the component with the boss ID. And in the third phase, you're going to prune out any insignificant component based on some threshold parameter, like really small components that are not important for the simulation. So we used Tram to aggregate all these messages in phase 1 and phase 2, and we tested and verified the correctness of our library with some protein structures that we borrowed from RCSB Protein Data Bank. And we also do some large-scale testing with some synthetic and real-world graphs. So to give more details about how we do this pruning, we need to perform some sort of a global reduction to gather the membership statistics across all chars for each component. So what this would mean is that each char would technically be building a map where it maps the entry of the component ID to the count of vertices on the char that belong to that component. And we would contribute all these maps to a custom reducer and do some sort of a map merging to find the final reduced map. And then we would broadcast these reduced final maps to different PEs, and then the vertices look up this local map on each PE and find out if it is pruned or not pruned. But this involves a lot of overhead, as shown here. So the red region indicates the amount of time that the algorithm spends in just inside the reducer to do the map merging operation, while the green region indicates the amount of time that the algorithm is spending in just rebuilding or reconstructing the map on each PE. So we wanted to avoid this sort of an overhead, especially something that we observed in large scales when we were learning on large number of nodes. And so we introduced an additional phase in phase 2, a subphase in phase 2. So before doing the labeling operation, we do some sort of a parallel prefix sum operation and find the total number of bosses that are currently present in your entire simulation. And we do this to relabel all our bosses with sequential identifiers. After doing this, you just continue with our original labeling algorithm, but relabel all your vertices with the new boss IDs with the sequential identifiers. Now in the pruning phase, for the reduction, instead of constructing complex map-based data structures, you would just build a fixed size array, since you already know the total boss count, and you'll reduce these arrays for a sum reduction. Note that these arrays can be sparse on different chars, but we noticed that this implementation is highly scalable for especially large number of node counts, and it has much lesser overhead compared to our previous implementation. So now moving on to the performance evaluation to give some performance numbers, we did various experiments, specifically with using some synthetic graph generators called the probabilistic mesh, which is a concept borrowed from cluster dynamics in computational physics. First kind of experiment that we did was to evaluate the phase runtime to find out which portion of the library is spending maximum execution time. And we used various mesh configurations ranging from 1 million all the way up to 64 million vertices. And we use different probabilities as well. Second, we do strong scaling experiment where we used two meshes of 64 million and 256 million vertices sized graph and a probability of 60%. And we increased the number of cores from 64 all the way up to 4K cores. And we also did some real-world graph analysis using COM-ORCUT, which is basically the social network graph, and COM-Amazon, which is the product correlation network graph. And these are pretty big graphs, and these were borrowed from the SNAP dataset available publicly. All these experiments were performed on the Blue Water supercomputer maintained by NCSA. So the first result is to show the phase runtime evaluation. This we did with a 1 million vertices graph on 64 cores, basically 2 nodes. And you can see that as I increase the probability, the amount of time that my library is spending in phase 1 is slightly more than the previous probability. This is because as you increase the probability, your graph is getting denser. There are more edges to process, which means more unions and find operations. So you tend to spend more time in your phase 1. Correspondingly, your time decreases in phase 2 because your number of components is decreasing, and hence the reduction operation becomes much faster. We see a similar trend for phase for 64 million vertices graph as well with 4K cores. You can see that we're able to do the entire simulation in under 3 seconds for a 40% probability itself. Now for some strong scaling analysis, we actually saw really good results for strong scaling both with 64 million vertices graph and the 256 million vertices graph. We are able to do the 256 million vertices graph on 4K nodes in just under 10 seconds. And one observation to note here would be that the amount of time that is being spent in phase 3 or the pruning phase for the 256 million vertices graph is more than 64 million, which is expected because you have way more number of components in the 256 million vertices graph. So for all those of you who were also here for my talk in last workshop, I sort of wanted to give a comparison to where we were standing last year and where we are right now. And this is some sort of a performance improvement evaluation. So last year when I presented, we were able to run 16 million vertices graph in a little under 2 minutes. But now for the same kind of core count, we're able to do it under 1 second. And for a 64 million vertices graph, which was taking about 3 minutes earlier, is now able to do it under 2 seconds for the same core configuration. And much of the heavy lifting has been coming from the path compression optimizations that we implemented, as well as message aggregation using TRAM, since it's a very fine-grained message algorithm. And the 256 million vertices graph, we were not able to run it in the previous version, but now we're able to do it under 10 seconds with about 4K cores. We also did some evaluation with some real-world graphs. So you can see how COM-ORCUT shows a decreasing trend with execution time as you increase the number of cores up to 1K cores. But COM-Amazon does not show promising results. It's a very sparse graph, and you can see that, in fact, the execution time increases as I increase the number of cores. So what we believe is that the irregular nature of some of these real-world graphs can lead to potential bottlenecks at some of the roots of your component. So consider the case when you have a very dense graph. One of your components that you're building is going to be really big. And the root of this component is going to face some potential bottleneck. So consider this case where you have an edge between vertex V3 and V1 and an edge between vertex V1 and V2. So in your later stages of phase 1, when you're processing these two edges, consider this component to be your biggest component. Boss 1 is going to be bombarded with so many find operations in the later stages, and is going to sort of be a serial bottleneck for just boss 1 to process it. Another problem that we sort of observed was there can be cases when the component roots are unevenly distributed among your chars, which can lead to some sort of an imbalance in our labeling algorithm, with some chars going ahead and some being held back by the others. So we are currently working on addressing these issues. Primarily, we want to optimize this phase 1 to remove all the bottleneck, and we are leaning towards implementing a decentralized union find algorithm. Thanks to Professor Edgar, we were able to come up with a formal algorithm for it, and I'm now working on implementing it and integrating it into our library. That should also improve our weak scalability performance right now. Also, I used this library and integrated it into Changa to perform the galaxy detection based on friends of friends algorithm. We have verified the correctness of our integration by testing with the test step benchmark, the 36,000 particle simulation, and we're able to get the right number of components with multiple different core configurations. So now we want to scale that up to larger problem sizes and larger Changa data sets. And lastly, we would like to implement some sort of a Python interface for this library using Champai, the motivation for which comes from the fact that cluster detection is central to various fields like machine learning and data sciences, where they use cluster detection to cluster their data. And the state of the art is something like DB-scan algorithm, but I believe this sort of an approach can also be highly scalable for the kind of data that is seen in these fields. The code and example is available publicly, and I'd like to acknowledge the grant that helped the part of this research. Thank you.
I just want to make sure I understand your bottleneck case. If you just explain sort of physically what's going on. Is this a situation where you have essentially, say, the majority of your vertices are connected into one group?
Big component, yeah.
And then just a few others, okay.
Yeah, so there you have these small components that you're attaching towards the end of your simulation or your phase one. So what happens is that the root of this big component is going to be bombarded with so many find operations or like requests, and that's sort of slowing down the entire algorithm. And so the idea that we wanted to avoid doing that is some sort of like a decentralized approach where we like go back and forth between the two bosses instead of just going all the way up on one, because you can make this guy point to this guy itself or this guy. That shouldn't be a problem. They all effectively come to the same component. You need not go all the way to the top. That's the approach, and we have a decentralized formal algorithm written down. We just need to implement this in code.
That's good, because that can frequently happen in cosmology, so good.
But I suppose you would typically have a large number of components too, right? And so if there are a large number of components, the bottleneck is not an issue if the component roots are spread to all the processors. And I just realized, I just thinking of this question, that the reason they may be bottlenecked on one or few is because your scheme for orienting pointers towards the smaller number might bias it towards, and your scheme for numbering vertices based on tree piece number followed by particle number would mean that many of the roots will be on the same char. So that may be a bias there that we can somehow figure out a way of correcting. Do you see that? I mean, tree piece 0 is likely to have lots of roots.
That's specific to the Changa integration that we did, because other algorithms,
that's true. That's true.
That's why you can see the mesh scaling much better, because it has the roots distributed very well.
Thanks.